So we've talked about torque, we've talked about moment of inertia, and we've talked about motors. Now I'd like to link all of them sort of together and talk about motors and torque and moment of inertia. First, let's just have a big reminder that power is the rate of doing work, so it is work over time. And please remember the power of a motor. You might remember this equation. I don't love this equation, but I know that this is the format you were taught from the Wildy textbook in second year. It is the speed of the motor, so omega times the torque over 9.55, but 9.55 is just our conversion from RPMs to radians per second, or from radians per second to RPM. Basically, 9.55 is 60 over 2 pi. Do you remember where that comes from? If you don't remember where this equation comes from, again, I like it in this format, but you know it in this format, I believe. I've just derived it here for you, so you can take this and read all the details. I won't step through every detail of the derivation of this equation, but most of my students do remember this equation from second year. Here's just an example. If you're a bit rusty using this equation, there's the torque and the angular velocity. What is the power? So that's the kind of thing that we can do with this equation. So this car engine must be a 25.1 kilowatt engine. It's the amount of power that is coming out of it. And here's another example where this one I'm giving you the motor turning in RPM, and we need to convert that to radians per second. So again, it's a sort of a review type of question for you, but please make sure that you understand the application of this question. And here, this one I'm solving for torque. And then I want to combine our knowledge of this moment of inertia with our knowledge of motors, this type of question where we can get torque. So a motor, basically, you have to put electricity in, and or in order to move a torque that is called the load. And we know that the relationship between the moment of inertia and the torque is related to the angular acceleration, but angular acceleration is the angular velocity over time. So if I look at this whole system, then basically I have a torque in and a torque out. So the difference between those, the torque of the motor that I'm basically paying for minus the torque of the load that I actually have to move something, is entirely dependent on the geometry of that system. So the mass and where that mass is placed, and the angular acceleration of how fast it is spinning right now. So here we're going to look at a flywheel again, but we're not just going to calculate the moment of inertia. We're going to calculate, we're going to use what we know about the torque, and we're going to see, well, how long would it take to increase the speed, decrease the speed, or turn off or turn on a system. In this case, we want to increase the angular velocity to 600. So then it was at 60, and we want to increase it to 600. So you can see where this is an applicable type of question. We could ask, say, for a wind turbine, we can say, well, right now it's spinning at a certain speed, and our next speed has to be 0. How much torque would that apply to actually braking the system? Or how much torque has to be applied by the force of the wind in order to get it up to synchronous speed? So that's where we're going with this. And here's another example of where we're calculating the power of some equipment, and then we're figuring out how much torque has been developed by that motor that we spent money putting that power into. And here at the end of this lecture, I'm just asking you, well, why do we care about this? Why did we talk about motors and talk about torque and talk about moment of inertia? And that's because in this course, we are doing energy systems of a rotational nature, and they do take energy to be put in with respect to time. So that's the power that we're going to have to calculate that is going to get them moving, whether it's from wind or water. And then there's a power that you have to use to stop them from moving in the case of wind. So that's how all of this relates.